Okay, guys, this is section 9.3 for Calc 2, parametrics and calculus. In 9.2, we learned about just parametric equations in general, graphing them and eliminating the parameters, mostly what we focused on, just to get an idea of what a parametric equation was. In 9.3, we're going to actually do some of the old calculus things that you learned how to do in Calc 1. You learned how to find slope and concavity of any function. Arc length is a formula that you probably learned whether you remember it or not. We did a lot of work with disk method and shell method, taking a shape and spinning it around an axis. This section of your book also does area or surface area. If you take a parametric and rotate it around an axis, I have yet to see that on a AP Calc question, so we're going to take that off the agenda and just focus on these three things. So a good standard problem would give you a set of parametric equations like this: x equals t plus 1 and y equals t squared plus 3t. Excuse me. Plus 3t. And they're going to give us a point, in this case t equals -1, where we're going to evaluate these amounts. The questions are to find dy dx, just find the derivative, because even though this function is defined in two parts, or this relationship is defined in two parts, in x and y, we would still like to be able to find the slope of the line if necessary. So we're going to find the derivative. We are going to find the second derivative. All right, which is slightly different than you might think. So there's just one little technicality to remember there. So part A, find the first derivative, find the second derivative, and then find the slope and concavity at the indicated point. So these are nice, solid Calc 1 topics that I could ask you to do with a polynomial anytime. We're just going to do this now with a parametrically defined set of equations. So let's start at the beginning, finding the derivative. The derivative of a set of parametric equations, it's no big deal. It's what you might guess it would be. Dy dx is equal to dy dt over dx dt. So the dt's just sort of cancel out and you're left with dy over dx. So you just take both derivatives and put one over top of the other. That's it. So even though this is within an example, this is a good, that formula needs to be in your notes somewhere. So dy dt, I've got y defined above. The derivative of y with respect to t is 2t plus 3. The derivative of x with respect to t is 1. So 2t plus 3 over 1, or just 2t plus 3. Okay, so there's first derivative. All right, and that derivative can be used to find the slope just like a normal derivative could. It'll give us the slope at any time t. I'm using time generically because it might not stand for time, but at any t value you want, you can find the slope. Okay, so part B, what's the second derivative? The formula for second derivative is not just 2. I'm not taking the derivative of what I just got with respect to t. I'm taking the derivative of what I just got as if it were my new function y, and I'm taking its derivative with respect to x. So the formula for the second derivative is going to be the derivative with respect to t of the first derivative which I did just find. That right there is what a lot of people think the answer is, just say 2. But that's not fully. I need to put another dx dt on the bottom. If you think about your answer to A as your new y value, then you take the derivative like before. Okay, so what I get this time is the derivative of what I just got, which is 2, over dx dt, which is still 1 from above. Now, I realize I just made a big deal about it saying it's not just 2 because that's the derivative up here, but by coincidence, dx dt happened to equal 1, so our answer is just 2. But it's not just the derivative of your first derivative. Please remember that. It's the derivative of what you just got with the same denominator as you had in the last part. So my second derivative is a constant 2. All right, so that's my first two parts. Part C is what's the slope? Well, you've known now for a year that if you want to find the slope, you plug into the derivative. So since my derivative is equal to 2t plus 3, my slope at t equals negative 1, which was the given t value at the beginning, is 2 times negative 1 plus 3, which equals 1. All right, so there's part C, my slope is equal to 1. And part D, what's my concavity? Well, my second derivative is what determines concavity. A positive second derivative means concave up. A negative second derivative means concave down. And this one is 2 always. It doesn't matter what t we plug in because there's no t to plug into. So this is always positive. So that means my graph is always concave up. So that's some just basic Calc 1 stuff that we are making Calc 2 by applying it to a parametric situation. So let's take a look at the picture just to kind of confirm some of this info. The equations we just graphed were t plus 1 and t squared plus 3t. Get a picture of it, and we get basically half of a parabola. We could eliminate the parameter and get the parabola, but if my t in question was t is negative 1. So I graphed that. My window was automatically set from like 0 to 25, which was from my last problem. But let's say I graphed it from, I don't know, t min. Let's say I went from like minus 5 to 5. So there is the rest of the parabola because my t was messed up. I didn't realize that was going to show up, but I'm glad it did. Watch your window. If your window is set a certain way from a previous question, you need to make sure that it's going to show your full graph because certain t's create the rest of the graph. All right, so there's our thing. And at 1, when t is 1, the point in question, let's see, or excuse me, when t is negative 1, our x would be 0, and our y would be, looks like, zoom in a little bit. This point right here is the point created when t is 1. So the characteristics of that point that we've been talking about, we said that the slope was equal to 1, and so you can kind of see that that's right there. It's at a 45-degree angle, and it's concave up because it's concave up everywhere. And a parabola that opens upward is concave up everywhere. So there is a picture of the graph. Okay, so next is, the last thing we're going to talk about is arc length. Arc length formula for parametric. This is one you do need to know. It's basically the x derivative squared, the y derivative squared, add them up in square root, and then integrate that from a to b. And a to b are the starting and stopping points, the starting and stopping t values for where we're going to begin our arc length. So this is just how long a piece of the graph is. So we're going to do these in the calculator. Most of them are written so that there's some sort of complicated integral that you can actually solve. I anticipate that this is going to be a calculator question, and we might end up doing some by hand, but for now let's just focus on the formula and typing it into the calculator. So here's my set of parametric equations, and my arc length is going from 0 to 1. Okay, so my formula calls for each derivative squared. So let's just go a little bit at a time. dx dt, if my function is the square root of t, that's t to the 1/2. The derivative of that is 1/2 t to the negative 1/2, or 1 over 2 square root of t. And my derivative of my y is 3, so that one's pretty easy. Now, you can square those, or you can just let that be squared in your calculator. So, here we go. Let me get out of, even though I'm in parametric, I'm going to just do this as if they were regular functions. So, it's kind of confusing because when I'm back in rectangular mode or function mode, my t value is actually x, but when I use my x button, I'm going to get an x instead of a t, but just follow along. So I integrate these with Math 9, FNINT. And the three things you need to plug in are the function, the variable, the a and the b value, the starting and the stopping points. I know some of you find integrals by using the graph, and that would be fine too, but I like this way. So the thing that I am integrating is a big square root. And underneath that square root are my x derivative squared and my y derivative squared. Okay, so my first thing is going to be my x derivative, which is 1 over 2 square root of x. Now that closes the little square root, because remember, if you're dividing, you need to divide by everything, otherwise it multiplies and you're going to get the wrong answer. So 1 divided by 2 squared of x, that closes the square root, that closes the denominator, and that closes the whole fraction. So I had 3 opening parentheses, I need 3 closing parentheses, and I'm going to square that. Okay, plus my y derivative, that was easy, that's 3 squared. Now that closes the big square root, so that's all my function. So try to keep track of all those parentheses, I know it's a lot. Next is comma x, because I'm integrating with respect to x. Next is my starting point 0, and finally is my ending point 1. So this is, the difficulty in here is getting all the parentheses typed in correctly. It's not, you're given the formula that you're going to eventually have to remember, but it's, the derivatives weren't hard, the squaring is done in the calculator. It's just a matter of getting it all entered in correctly. So, calculator tells me this arc length is, thinking, still thinking. Come on, calculator. 3.249. And if you had, this one you actually could have worked out. It would have been a difficult integral with natural logs and all that. And there's an expression for it, but it ends up equaling 3.249 in the long run anyway. So we're just going to stay with that. So I'm going to cut this off. The things to know from today are the arc length formula and just some nice Calc 1 skills applied to parametrics. Pay particular attention to this formula because it causes some problems every year. Okay, so I'll see you in class. I'm out.